The third unit in this course is about inequalities, and the honors topic for this particular unit is a little bit of a further enrichment, a little bit beyond what we're doing in class with inequalities. There's two phases. There's solving compound inequalities, which are things that look like this, where there's more than one inequality symbol in the same expression, or equation or inequality statement, and then absolute value equations. We'll start with this first part, just to get a sense of what we mean by a compound inequality. And usually, and you'll talk about this in class, and you've already learned about this a little bit, the idea of graphing an inequality. Like simply, x is less than 3. When we graph an inequality, what we're doing is we're showing visually where all the solutions to that inequality lie. If it was just x equals 3, then 3 is the only answer. But if we have that x is less than 3, that means there's multiple answers. 0 is less than 3, so x could be 0. Negative 10 is less than 3, so x could be negative 10. In fact, there's an infinite number of numbers that are less than 3, and so we can't possibly list them, so we just show what they look like in a picture. And you already most likely know how to do this. We make a little number line, and we label it, so 0, 1, 2, 3, 4, 5. Just make sure that there's some numbers to the left and some numbers to the right of whatever your boundary number is. Now we do need to show that x is less than 3. 3 is the boundary mark. I don't want 4, I don't want 5. They're not less than 3. And I have to show that not only is 3 the boundary, but it's a less than. It's not a less than or equal to. There's no little line underneath it. So I need to show that 3 is the edge of my graph, the boundary, but it doesn't actually include 3. My graph does not actually include the 3. So hopefully you remember how to do this. We do this by showing an open circle on the 3. And then we say, well, again, 4 is not less than 3, 5 is not less than 3, but 2, 1, and 0 are, and so is 0.5, and 1.2, and 2.9, and all those other decimals. And so I show that I'm going off to the left here, off the edge, and continuing on. And so this is my graph of x is less than 3. I have an open circle on the 3 to show that 3 is the edge, but I'm not including it, and then a graph, an arrow to the left. So when we have compound inequalities like this, like these two here, it works the same general way. The way that we go about this is the same general principle. I create a number line. This time I want to make sure that it includes both 1 and 3. So again, I'll just do the same thing. 0, 1, 2, 3, 4, and 5. Now, this is showing me that I have two boundary points. I have a boundary point at the 3, and I have a boundary point at the 1. How I could read this is 1 is less than or equal to x, which is less than 3. Which means I actually have two inequalities going on here. I have that 1 is less than or equal to x, and I have that x is less than 3. Now this 1 is less than or equal to x here might be a little bit more sensible to rewrite if I turn it the usual way, have the x out in front. So what I'm saying is that x is greater than or equal to 1, and also x is less than 3. So I can treat these two things independently. I have that x is less than 3. I put my open circle on the 3, just like I did before. And I have to show that x is greater than or equal to 1. So 1 is another boundary point, but I'm including that 1. So I show that I'm including it by doing a closed circle, a filled-in circle. Now to finish this graph, I have to keep in mind that this is an and statement, that I'm saying that 1 is less than x, or rather x is greater than or equal to 1, and also less than 3. So 0, for example, is less than 3, but not greater than or equal to 1. And 4 is greater than or equal to 1, but it's not less than 3. So I can't have 4, and I can't have 0, and I obviously can't have 5. But 2 is both greater than 1 and less than 3. And so again, is 1.1, 1.2, 2.3, 2.4, 2.5, all of those other decimals in between. And so then to make my graph, I just connect those little dots. If you remember old cartoons, they showed like these dumbbells, the really big heavy weights that people lift. That's the kind of the picture that we have here. We got two little circles on both ends, and then a bar connecting the two of them. Now for an OR, again, it's the same general setup. use my same number line. 0, 1, 2, 3, 4, and 5. And now I'm showing that x is less than or equal to 1, or x is greater than 3. And we have to say an or in there because it can't be an and. You can't have a number that's both less than 1 and also greater than 3 at the same time. They contradict each other. So what that means is, well, the circles aren't going to be connected, for one thing. It means that we just graph them individually. So x is less than or equal to 1 means I put a closed circle on the 1, and then an arrow going to the left to show that I want x to be less than or equal to 1. And then I'll do the other one in blue. X is greater than 3, open circle on the 3, because I'm not including the 3 again. And then an arrow going to the right. And this overall graph, these two parts, to the left and to the right, that's your solution set. What I'm saying is that x could be 4, it could be 5, it could be 0, it could be 1, it can't be 3. But any of those numbers that I've included in the shaded region there are possible solutions. And so they are included in the solution set. They're graphing the graphs of the answers, the picture of the answer we have right there.